All right, so we're gonna be using the water tubes, and there should be one near each of the traditional groups. We're gonna be sending sound waves down the bottom, to the bottom of the tube, or to wherever the water level is. So the sound wave's gonna come down, hit, and then bounce back up. So if I have two waves so the waves coming down are gonna meet with the waves coming up, and so they'll interfere with each other. So if I have a wave traveling along like this, and a wave traveling like that, what's gonna happen when they meet?
They're gonna collide.
They're gonna collide.
They're gonna collide and make what?
They're
Well,
gonna turn into one wave.
Okay. And what can you tell me about that one wave?
It's
two nodes.
Well,
Theoretically.
the way I've drawn it right here, we're not really worried about nodes at the moment. So the one wave, would it be, let's see, that's.
Wait a second, actually, they're on the same side, aren't they?
Yeah, they are
So
on the
one
same
will
side.
get reflected opposite to the full wave, right?
Oh, does one be down here?
Yeah.
It depends. When they join, are they gonna join something like this? Or something like that?
Ooh, are they gonna go higher?
I think like the second one.
Okay, the larger one?
Yeah.
That's known as constructive interference. The idea that you can just add the waves together is this idea called superposition, but more of a side note there. All right, so they're gonna join to create something bigger. Now, if I have a wave coming in, yeah, I guess that can be seen. Not really. If I have a wave, wow. Just have to draw on the right surface there. A wave coming in like this, and a wave coming in like that.
They're
What
gonna
happens?
turn into a straight line, right?
If they're indeed the same height, yes.
Yeah.
So nothing shows up. So if we take into account how fast the wave is traveling, it's gonna hit this spot, bounce back, and if this height, air column height, is the right length for the frequency and the temperature or speed of the wave, then we will get harmonics. Is harmonics a new concept? Does the word sound familiar?
No.
No.
Okay. Well, partly you'll hear it in a moment. So if we're dealing with sound, which is what we're dealing with today, if we have it where it adds together to make something bigger, how would we notice that? If we're talking about sound, what does a bigger sound wave sound like?
Is it higher pitched?
Not a higher pitch.
So it'd be the opposite?
No, it's not a frequency thing.
Okay.
What did you ask?
For a sound wave, if you got hit with a sound wave and then you got hit with a sound wave that was twice as big, how would we notice the difference?
You would feel it.
Yeah. Wouldn't you feel it?
Are you feeling the sound right now?
Well,
No, I mean,
no.
yeah.
I'm thinking about
Well, I
like
mean,
for
you go to
some
a
reason I'm
concert,
thinking about
you know.
ocean wave.
What do you get?
I don't know why.
That ultimately, yes. Whether you feel it or not is up to you. There sometimes, if it gets like a sonic boom, you not only have two waves, you have a whole bunch of waves getting together to create this huge thing. So you would
Yeah.
feel a sonic boom, but normal speaking, I guess it depends on how sensitive you are. But ultimately, it's louder. So what we're looking for here is sound's going to be coming down, bouncing, and coming back up. We want it so that we get this big constructive interference here, and at the bottom should be destructive interference. And also, as a side note, when you have a harmonic, if there's a fixed end, which would be this, and a free end, the fixed end should be a node where there's complete cancellation. And the free end should be an antinode, which is where you've got the biggest, you get something like that. So when you send sound waves down to the water and it bounces back, you're going to be trying to find the height at which it sounds the loudest. for a particular frequency. So the first harmonic, well, actually, let's start out before we get to the first harmonic. A wave, did anyone hear that trig? All right.
Yeah.
When you do a plot of a sine wave, how far out do you usually go?
It's been a long time. We didn't go very far out now.
I think it was 2 periods, wasn't it?
It was.
So how long is one period?
Pi. Oh, 2 pi.
2 pi, yeah. So a full wave, what I was heading towards was a full wave looks like that. That's a full wave. If you're dealing with harmonics, generally you would draw it like that. This would ultimately be a second harmonic. But that's what a full wave looks like. Well, for the water tube, as sound comes down, it comes bouncing back. The simplest pattern is you have an antinode at the top. These are antinodes here. And these are nodes.
I
You
understand.
did the vibrating string last.
Yeah.
Okay.
Yeah, we know.
All right. Sorry.
No, you're fine.
So the simplest pattern here would be something like that. This is some length L. I got a node, I have an antinode. Well, how many waves is that?
1? No, it's half of 1.
Half of one.
No, it's 1.
One would have look like that, or potentially that's also one wave.
So it's half of 1.
Half of one would look like that or that.
So it's just 1.
So that's 1.
You keep going back up. It's not one.
Oh,
It's
is
0.
it 3/4?
It's a quarter.
It's a quarter.
Oh.
1
Just one quarter. That's a quarter of a wave.
I'm thinking.
Basically-
Oh, I could've let you finish up.
I was confused because the first wave you did.
So this, basically, you're going from a node to an antinode. It's a quarter of a wave. I just stretched it out. So the first harmonic should happen at a quarter of a wave. So this length, this would be the height of the air column, the length is equal to a quarter of a wave, which means that the wavelength is 4 times the length of the air column. The next harmonic is actually not the second harmonic here, it's called the third harmonic. The next simplest pattern we can, standing wave we can get, would basically look like that. How many waves is this?
What, 1?
Still
No.
not one.
Half?
75%.
There we go,
Okay.
or as Chelsea said before, 3/4. So the length this time, this is the length, that's 3/4 of a wave. And the fact that there's a 3 there instead of the 1, that's why this is called the third harmonic. I didn't come up with a naming system. So the wavelength is 4 times the length over 3. Sure I did that right. Yep. So you'll be finding the first and third harmonic by getting a particular frequency, putting the frequency down into the tube. You'll be using the LabQuest to generate sound. The sound gets to the bottom, bounces back up, and you'll vary the height of the water column, which varies the height of the air column, to try to find the first and third harmonics. Then you will graph it, and then find the speed of sound.
Wait, so how do we know when we find the first harmonic and the third?
All right, let's just run a quick example here. And again, faced with this, at one point, we had a whole bunch of these jars here. I never know why they always have these.
I know, they're so
Yes.
strong.
You so you can clean out things better.
It's possible.
Get some good force in.
Yeah, but you
I
only
don't
need
know,
one.
but I use it and it's like.
All right, so the
Yeah,
mechanics
I've
of it
broken things and missing the force. It's fine.
is you don't pour water into the skinny tube, you pour it into this. As I lift this, it's going to be metal scraping against metal. It can be piercing. You can see water coming in down there. So basically the water is going to rise, this is going to lower, and then when they're at the same height, it's going to stop. This is exciting. Yeah, probably. Well, that's living out, leveling out. Let me grab some more water.
I feel like I'm watching a loading screen. Tank drawing just didn't seem as accurate.
All right. So the water level here and the water level here are roughly the same. This is called the reservoir, by the way. So by lifting this up, I can raise the water level.
Can you do the opposite?
And then if I just lower this,
Wow. That's so cool.
all right, that doesn't help you identify where the first and third harmonic are. So let me grab the tuning forks.
So
I used to,
easy
I
use.
remember hitting people's knees with those when I was younger.
Knees.
All right, this is the 320 hertz tuning fork. You'll be using the LabQuest instead of this, but. Ah. I thought I'd hit it.
Wow, that's like playing the water cups.
Hear how it got louder there?
Yeah.
As it passes by that just the right length.
So the height where you hear it, that's what we're gonna be recording.
So the first one you hit is going to be the first harmonic. The next one you hit should be the third harmonic.
Okay.
Now, here's one of the trickiest parts about this lab. There are false harmonics. So if I started at between nothing and the first harmonic, it's going to get slightly louder, and then it's going to come up, go back down again, and then the first harmonic is going to be louder than that slightly louder part. So you got to watch out for that. If if you have some rough idea of the speed of sound, roughly 340 meters a second, and then you divide by the frequency, so 340 divided by 320 is a little bit more than 1. The first harmonic should happen at a quarter of that. So the first harmonic should be somewhere around 25 centimeters, just as a crude estimate. So if I get my first harmonic at 10 centimeters, if I think that's it,
It's a false.
it can't be. That's a false one. So it's one of the few labs where it might be beneficial to figure out what the answer is supposed to be first, and then pick the one that's closest to that.
Plus percent here.
So right now, that's a 27. And for these, if you're using tuning forks, in theory, this is supposed to work. Alright, so that was somewhere around this part right here. There is a gap between the top and 0 here, and so one of the first things you do, so I was reading over it before I printed it out, the wording was awkward. You're finding the length between the top of the tube and where 0 is, but if I add, it's roughly 2 centimeters, if I add that 2 centimeters to it, it puts it at about 26.5 centimeters for the length of the air column for the first harmonic.
So it's approximately 25 centimeters plus the approximate 2 centimeters from the top.
Well, I mean, if that 25 were accurate, again, that was a crude estimate, if the 25 were accurate, then it should have peaked at 23 here, plus the 2 would get us 25.
Gotcha.
All right, you will also notice, it should be revision 2, not revision 1. Version 1, there could be some errors in here, so if you have questions, please ask. Questions at this point?
Do you have a thermostat in here to tell the temperature? Or is it? Oh,
This is the temperature in degrees Celsius. You would add 273.15. So temperature, I think we should call that one trash.
Let's say 20.
Let's see how long I can carry around in my pocket. So if I have the degrees Celsius, I add 273.15 and I get Kelvin. All right,
It says you want it in Celsius, so.
does it?
Temperature of the room in degrees Celsius.
Oh, yeah, you record it in degrees Celsius, but when you do the calculation for equation 1, so analysis number 1, you'll need to get it in Kelvin.
it's divided
Oh,
into
okay.
3.15
Or,
So what's the temperature?
Kelvin.
I can't, it says 21.5.
21.5 degrees Celsius right now.
You said how much? 23?
Nope, that's like the degree.
No, 21. 21.5.
It put the degrees. Again.
All right, I think we're ready to rejoice,
Cool.
because as you know, it is physics.
It is. Isn't this our last week of this class?